Graphing polynomial functions. When we graph a polynomial function, they are classified by their degree. The graphs of polynomial functions are classified by the degree of the polynomial. Each graph, based on the degree, has a distinctive shape and characteristics. So this week, you're going to be writing, for example, you might get, by the end of this week, you should be able to, oops, let me make this a little bit thinner of a line here. Okay, so by the end of this week, I should be able to give you a graph, something like this, and you should be able to write a polynomial function for this. Now, it is not going to be the exact polynomial function for this, but it will be a polynomial function that will replicate this function. So if I graphed it out, it will give me the same shape. It won't give me the exact answer, but it will give me the general shape of this graph. And then you will also be able to graph polynomial functions. So for example, if I gave you y is equal to x to the fifth, well, I'll write it this way, x plus 4 to the second times x minus 3 to the first times, x plus 4. You should be able to graph you'll be able to graph this function. Now, it's not going to be exact, but you will get the general idea of how to graph these functions, so you should know what they look like. Okay, and the first thing we have to do is we have to be able to tell, look at a function and be able to tell what the degree is, the function is. So the end behavior is a description of the values of the function as x approaches infinity, positive infinity, and negative infinity. The degree and leading coefficient of a polynomial function determine its end behavior. It is helpful when you are graphing a polynomial function to know about the end behavior of the function. These are the four graphs that I have memorized in my mind because all end behavior always represents the same thing. For example, if you had a positive leading coefficient, okay, and let's review coefficients. This is a coefficient. It is a number in front of the variable. So if the leading coefficient is positive and the power is odd, then the end behavior will always look like this. The end behavior, and we would say, okay, so this is positive infinity here, this is negative infinity here. So we would say that as x approaches positive infinity, y approaches, because this is my y-axis, what's happening to the graph? As x gets larger and larger, what's happening to the graph? Well, the graph is going positive infinity. As x approaches negative infinity, what's happening to the graph? Well, it's going to negative infinity. And that happens to all graphs that have a positive leading coefficient and an odd exponent. So if I gave you a graph that looked something like this, y is equal to, let's say, 5x to the fifth. Well, it has a positive leading coefficient and an odd exponent. I don't know what this graph is going to look like, but I do know that at the very end, okay, so it might look something like this, but I do know at the very end, the end behavior is going to be going down to the left side, and it's going to be going up on the right-hand side. That is what the positive, or the leading coefficient being positive, and the odd. And you can go to Desmos, and you can plug in any function that you want. Okay, so let's say I did go to Desmos. Okay, so I got to plug in, okay, because it always gets to my mind. It's like, oh, okay, maybe kids don't understand this. So let's just check it out. So I'm just going to turn on the Desmos calculator. Okay, I'm going to have to share that with you guys here so you guys can see the same thing that I'm seeing. Okay, so I'm going to share Chrome tab, Desmos graphing calculator. Boom. Okay, so I'm going to plug in a function, y is equal to, and as I said, it's going to have a positive leading coefficient and x raised to the and a negative exponent. So here's what the graph looks like. Look at the end behavior. The end behavior is exactly what I said it was going to be. It's going to go down on the left-hand side, up on the right-hand side. Let's try another one. Let's try y is equal to, again, we want a positive 7, and then x raised to the, let's say, 7th power, raised to the 7th power. Well, there it is again. Now, I could do different graphs that are going to look way different, but I know they still have. So let's go 2 and then x plus 2. Let's go squared here. Oops, that didn't go squared. Squared. I want to make it an odd. So now this is an even, so I'm not done yet. So let's just put another function in there. X plus 4 raised to the, so I want to raise it to, let's say, the third, because now this will give me a 5th degree polynomial, because I have 2 degrees here, 3 degrees here. That's a 5th degree polynomial. It's this green one here. What's happening at the end? It's going up at the, as I go farther to the right, it's going down. I don't look at the inside here, and we're going to be talking about where it crosses the x-axis in a little bit. But the end behavior is what we're looking at right now. And anytime it has a coefficient, a leading coefficient that is positive, and an odd exponent, it will always go up on the far right and go down on the far left. That is what the end behavior tells us. Okay, so let me get back to my files, and you can try this. And I always suggest trying this stuff with Desmos calculator, because if you don't, Desmos calculator is such an awesome thing that you can check things out real quickly. All right, I'm trying to find my lesson plan. Oh, it's way up here. All right. Okay, so you can always try it out. It will work. So now, if the leading coefficient is negative and the exponent is positive, it will always go up on the left-hand side. So as x approaches positive infinity, y approaches negative infinity. So it's going down here. And it will always, it doesn't matter what polynomial we have, as long as the leading coefficient is negative and the exponent is odd, the end behavior is going to look like this, always. So I could write an equation, y is equal to -5 x to the 7th. It's not going to look like this. It might look something like this, but I do know what the end behavior is going to do. The end behavior is going to go up on the left-hand side. It's going to go down on the right-hand side. And then if I have a positive exponent and a positive coefficient and an even exponent, then it's going to go up on both sides. And if I have negative leading coefficient and an even exponent, it's going to go down on both sides. That is what happens to the end behavior. We don't know what's happening in the middle of the graph. We just know what's happening at the end of the function. And that's why I always just memorize these 4 graphs, because I know what 1x is. It's a linear function, and I do know that it's going up, so I know what the end behavior looks like. So that's why I use these 4 graphs, because it always works. So now here's what our book gives us, okay, the definition. And again, it's the same thing. If a is greater than 0, so that means the coefficient is positive, and I have an odd degree, it's going to go up on the right, down on the left. If it's an even degree, it's going to go up on both sides. If the leading coefficient is negative, that means a is less than 0. It goes up on the left, down on the right. If it's an odd degree, if it's an even degree, it's going to go down on both sides. So those 2 slides are basically the same. So it says identify whether the function graph has an odd or even degree and a positive or negative leading coefficient. Well, it's going up on both sides. So I always go back to my 4 graphs, and I look at it and it's like, okay, that one, the end behavior looks exactly like this. What is this graph? This is 1x squared. So the leading coefficient, here is positive, and the exponent is even. I know that. For this graph, I know that the leading coefficient is going to be positive and the end, or the exponent is going to be even. I don't know what it is. It could be to the, this graph could be like 4x to the 4th power. I don't know. All I know is that this is going to be positive and this is going to be even. Okay, that's all we know. We don't know anything else. We will get a little bit farther ahead in a little bit, but that's what I need you to know right now, how to find the end behavior. So it says identify whether the function graph has an odd or even degree and a positive or negative leading coefficient. Okay, so if I go back to my graphs, it looks like this graph, right? That's what the end behavior looks like. It's going to go up on the left-hand side, down on the right-hand side. So that graph was negative 1x to the first. So I know this graph, the leading coefficient is negative. I know that. And I also know that the exponent is odd. Okay, so it really could be, this graph could really be like negative 5x to the third. I know it's not negative 1x to the first because that's a linear function. This is definitely not a linear function. And I don't know this is correct. The only thing I do know is the leading coefficient is negative and the exponent is odd. That's what I know, and that's what I need you guys to understand, okay? Because then that's going to lead into a little bit more stuff as we go on. So in this one, it says identify whether the function graph has an odd or even degree. Okay, again, this one is very similar to the two graphs ago. Looks like this one, right? So I know it has an even power, and the coefficient is positive. Okay, just by looking at what's happening at the end of the graph, I know what the leading coefficient is, and I don't know what the leading coefficient is. I know it's either positive or negative, and I do know that the power is going to be even. Identify the leading coefficient, the degree, and end behavior here. Okay, the degree is always the highest power. So in this problem, the degree for this problem is 4, and that's even, right? That's an even number. And the leading coefficient is negative 1, because there's really a 1 in front of here. So I do know a little bit about this graph. I know that's even and a leading coefficient negative. I know this graph is going to, the end behavior is going to go down on both sides, right? I don't know what the rest of the graph looks like. It might look something like this. But I do know at the very end, the end behavior is going to go down. And that's what we need to focus on right now. And this is what this graph really looks like, right there. So yes, it does go down on both sides. All right. Now, if you take a look at this, now we're going to talk about multiplicity of graphs. The solution of a polynomial function is where it crosses the x-axis. So I'm looking at this negative 3, negative 1, and 2. Those are pretty important points in this graph. So now let's take a look at what it really means. It says graphs behave differently at various x-intercepts. Sometimes the graph will cross over the x-axis at an intercept. Other times the graph will touch the x-axis and bounce off. So like for here, touches it, comes back up. Suppose for the example, we graph the function x plus 3. So this is the graph of x plus 3, x minus 2 squared, x plus 1 to the third. Now, we've learned before that if we solve a polynomial function, that if it's factored out, and we'll have all of our problems tonight are going to be factored out, that wherever the factors are equal to 0 is a solution, and it's where it crosses the x-axis. So I know that this graph is going to cross at negative 3, it's going to cross at positive 2, it's going to cross at negative 1. Now, it might not cross because this is the exponents are going to tell us what's happening there, okay? So notice in the figure below the behavior of the function at each of the x-intercepts. This is first degree, right? X plus 1 to the first degree. It just crosses over real nicely. Here I have a second degree at positive 2. And look at that. It doesn't really cross real nice, does it? Oh, positive 2 is right here. So it hits and comes back up. And at a third degree, it looks like it hits here and goes up. So it doesn't cross nicely. And all of those those degrees really tell me what's happening at this. And these are called multiplicity, okay? Because this is 3, 2, 1. This is a 6th degree polynomial. Why do I know it's a 6th degree polynomial? Because there's 1 degree here, 2 here, 3 here. This is a 6th degree polynomial. So that means it has 6 solutions. what are the solutions to this problem? Well, we already said -3 is a solution. 2 is a solution, but guess what? There's 2 of them. Because this is to the second degree, that means if I really wrote this out, it would be x plus 3, and then x minus 2, x minus 2, right? Because that's what the second degree means. X to the third, or x plus 1 to the third, really means x plus 1, x plus 1, x plus 1. So really, there's 3 -1s as solutions. So 1, 2, 3, 4, 5, 6. There's 6 solutions to this problem. And I knew there had to be 6 solutions because it's a 6th-degree polynomial. 6th-degree polynomials have 6 solutions. A 4th-degree polynomial has 4 solutions. Okay, so now how do we tell if it crosses nicely, or if it hits and goes up, or if it hits and doesn't cross? How do we tell that? Okay, so this is how you do that. The x-intercept, x equals -3, is a solution of the equation x plus 3 is equal to 0. The graph passes directly through x at -3. The factor is linear and it has a degree 1. So the behavior near the intercept is like that of a line that passes directly through the intercept. We call this a single zero because the 0 corresponds to a single factor of the function. So anything to the first degree is going to cross nicely. The x-intercept, x equals 2, is a repeated solution of x minus 2 is equal to 0. The graph touches the x-axis at the intercept and changes direction. The factor is a quadratic, degree 2, so the behavior near the intercept is like that of a quadratic. It bounces off the horizontal axis. The factor is repeated. It appears twice. The number of times given the factor appears is called the multiplicity. The zero associated with this factor x equals 2 has a multiplicity of 2 because the factor x minus 2 occurs twice. Now, the x-intercept -1 is a 3rd degree. The graph passes through the axis, and so a 3rd degree will hit the axis, but it will go through. So now, when you start thinking about it, what is the rules? The rules say that 1, a single, just crosses. Anything that has a 2 is going to hit and go up, and 3 is going to be up. But then this is where it gets interesting. For higher even powers such as 4, 6, and 8, the graph will still touch and bounce off. So all of them will look very similar to 2. So 2, a 4, a 6, and 8, they all are even. They all hit the x-axis and bounce up or down. I mean, it could actually look like this if it was a negative in front of that. And then 5, 7, and 9 will all hit and then go up. Okay, so that's what the multiplicity tells us. So now we're going to start looking at graphs. Okay, so here it says use the graph of the function of a degree 6. So this is a degree 6 polynomial function, and their possible multiplicity. So they want to know what the multiplicities is. Well, here it hits and bounces up. So I'm going to say that the multiplicity here is going to be 2. So if I was going to write, I'm going to write an equation for this thing. So x plus 3 squared. Now, why did I do plus 3 instead of minus 3? Because remember, when we factor, it's what makes this, the solution is what makes the factored form equal to 0. So -3 is a solution. That's my solution. Okay, here at -1, it just crosses 1 time. So I know that's a power of 1. So that's x plus 1. Here at 4, so now I know it's going to be x minus 4. And it hits and goes up. So I know it has to be either 3, 5, 7. However, we know we already have 2, 3. We already have a 3rd degree polynomial here. So this has to be 3, right? Because they said that this is a 6th degree polynomial. So here's my equation for this thing. X plus 3 squared, x plus 1, x minus 4 to the 3rd power. Now, if you don't agree with me, which a lot of you are going, oh, Mr. Frank, what are you talking about? That's not what that graph looks like. Plug it into your calculator. plug this into Desmos calculator. See what it gives you. It's going to look very similar to this. Now, it might not go down to negative 170 because I don't have a number out in front of here. I might put, I might have a 100 here or whatever, but we'll just leave it. I do know that the power in front of here has to be positive, right? Because it's going up. So I know that's a positive and an even degree. So that's how we write polynomial functions for something that's really crazy looking. So here is, and this is, they talk through exactly what I just did here. So if you want it written down, that is it. So if we wanted to sketch the graph of a polynomial function, what we want to do is we want to find the zeros, and we want to know what the end behavior is going to look like. Those are things that we can do. So let's take a look. If I wanted you to graph this, well, this is x. Turn my mic or my thing on. This is x to the first, 5x plus 2 to the first, because there's no powers on them, so I know, and x minus 4 to the first. So this is a third-degree polynomial, third degree, and the leading coefficient sure looks like it's positive, right? Positive leading coefficient. If I multiply this all out, it would be a positive leading coefficient. So I know that it's going to look something third degree, so it's going to look something. The end behavior is going to look like this. It's going to go up on the right-hand side. It's going to go down on the left-hand side. So if I'm going to graph this thing, let's see here. So 0 is a solution. Negative 2/5 is a solution. And positive 4 is a solution. So I know it's going to, here at 0, I know at 4, and I know at negative 2/5. I know it's a third degree polynomial, so I know that this is what my function is going to look like. So if I'm going to graph this thing, it's going to look something like, and that's what my graph looks like. Now, it's not exact because I don't know how far. I could plug a few points in to figure out all the points, but I know the general shape is going to look like this. Oh, Mr. Shanklin, you're crazy. It's not going to look like that. Okay, I'm gonna write this down. 5x plus 2, and then x minus 4. Okay, I'm going to go to Desmos calculator. I'm going to have to share this with you first. Desmos calculator. And I'm going to plug that in. I'm going to plug this equation in. So let's get rid of these. Okay, and my equation was y is equal to x, 5x plus 2, and okay, and there's my graph. Huh, kind of looks like what I had, doesn't it? Comes up, goes back down, comes back up. Now, I didn't know how far down it went because I didn't put any numbers in there, but the general shape, and that's what we're looking for tonight. We're looking for the general shape of the function. And my general shape is exactly what that function looked like. All right, that is it for this week. Hopefully you come to Monday's main lesson, and we'll go through all the practice problems. You guys have a great week. Bye.